A quantum antenna opens the terahertz frontier. Physicists at the University of Warsaw have demonstrated a fundamentally new way to detect and precisely calibrate terahertz frequency combs using a quantum antenna built from Rydberg atoms. By combining atomic electrometry with an ultrasensitive terahertz-to-optical conversion technique, the team achieved the first direct measurement of an individual tooth of a terahertz frequency comb, an achievement that had remained beyond the reach of conventional electronic and optical methods. The work, carried out by researchers from the Faculty of Physics and the Center for Quantum Optical Technologies at the Center of New Technologies, addresses one of the long-standing challenges in terahertz science. Although recent years have seen major progress in generating and detecting terahertz radiation, accurate calibration in this spectral region has remained elusive. In particular, while the overall spacing and total power of terahertz frequency combs could be measured, resolving and quantifying the power of a single comb tooth was considered impractical. The method reported in Optica now overcomes this barrier, transforming the terahertz band from a poorly accessible region into one amenable to precision metrology. Terahertz radiation occupies the boundary between electronics and optics, lying between microwaves and infrared light. This region of the spectrum is highly attractive for applications ranging from non-invasive inspection and molecular spectroscopy to next-generation wireless communication technologies, such as 6G. Yet its intermediate position has also made it difficult to handle. The oscillations are too fast for standard electronics and too slow for direct optical techniques. As a result, many of the precision tools that revolutionized optical and radio frequency science could not be straightforwardly extended to the terahertz domain. Among the most powerful of these tools are frequency combs, often described as ultra-precise electromagnetic rulers. Rather than providing a continuous signal, a frequency comb consists of a series of evenly spaced spectral lines whose frequencies are known with extraordinary accuracy. By matching an unknown signal to one of these teeth, its frequency can be determined with exceptional precision. Frequency combs underpin modern timekeeping, spectroscopy, and metrology, and their developers were awarded the Nobel Prize in Physics in 2005. Extending this concept to terahertz frequencies promises similarly transformative capabilities, provided that the combs themselves can be measured and calibrated with sufficient accuracy. The Warsaw team achieved this by turning Rydberg atoms into quantum antennas. In their experiment, a gas of rubidium atoms was excited with lasers so that one electron in each atom occupied a very high-lying orbital, creating a Rydberg state. Such atoms are extremely sensitive to external electric fields, including terahertz radiation. Crucially, by tuning the excitation lasers, the atomic response can be made resonant with a specific frequency, allowing the detector to selectively respond to a chosen spectral component. In standard Rydberg electrometry, the electric field strength is inferred from Outler-Town splitting, a quantum effect that depends only on fundamental atomic constants. This provides an absolute, self-calibrated measurement, in contrast to classical antennas that require external calibration. The approach is also remarkably versatile. The rich energy structure of atoms allows the same sensor concept to be tuned over an enormous range of frequencies, from static fields up to terahertz waves. On its own, however, atomic electrometry lacks the sensitivity needed to detect extremely weak terahertz signals, such as those carried by individual comb teeth. To overcome this limitation, the researchers integrated a terahertz-to-light conversion scheme, originally developed at the University of Warsaw. In this hybrid approach, the weak terahertz signal is coherently converted into optical photons, which can then be detected using single photon counters with very high sensitivity. This combination preserves the absolute calibration of the atomic method while dramatically enhancing detection capability. Using this quantum antenna, the team was able to tune sequentially to individual teeth of a terahertz comb and directly measure their intensities. Several dozen comb lines were resolved across a wide range of frequencies, enabling a full and precise calibration of the comb based solely on atomic properties. This marks the first time that a single terahertz comb tooth has been directly measured measured and calibrated. Beyond demonstrating a new detector, the work establishes the foundations of terahertz metrology based on quantum standards. By extending the principles of optical frequency combs into the terahertz regime, Rydberg atom sensors provide a route to reference standards for emerging terahertz technologies. Importantly, the system operates at room temperature, avoiding the need for cryogenic cooling and significantly improving prospects for practical deployment and commercialization. The work, conducted by Wiktor Krokos, Jan Nowosielski, Bartosz Kaza, Sebastian Borowka, Mateusz Mazelenik, Wojciech Wasilewski, and Michał Parniak, was supported by the Foundation for Polish Science and the National Science Center. Their results suggest that the once inaccessible terahertz region can now be explored with the same precision that revolutionized optics and radio science, opening the door to both fundamental discoveries and advanced technological